This lesson is all about the Hypotenuse Angle Theorem, or HA Theorem, which allows you to prove congruence of two right triangles using only their hypotenuses and acute angles. Before we start, let's make sure we have a firm understanding of right triangles. A right triangle always has one right or 90-degree angle. This means the other two angles must be acute or less than 90 degrees. We know this because all interior angles of any triangle must add to 180 degrees, and subtracting the one right angle from 180 degrees leaves only 90 degrees, to be shared by the two remaining angles, making both of them acute angles. Now that we have right triangles right in our heads, let's look at the HA or Hypotenuse Angle Theorem. The HA Theorem states, if the hypotenuse and an acute angle of a right triangle are congruent to the hypotenuse and an acute angle of another triangle, then the two triangles are congruent. Congruence does not mean just somewhat alike. It means the two triangles will be identical, every side and every angle equal between the triangles. Here are two right triangles, triangle ZAP and triangle HOT. They are both facing with their hypotenuses to the right. Notice angle A and angle O are right angles, indicated by the little square tucked into the interior angles. We are told that the hypotenuses ZP and HT are congruent, which is why they have the little matching hash marks. We are also told that acute angle Z and angle H are congruent, shown by their own hash marks. If we knew only that much geometry, we would be stumped. We could say the 6 parts, 3 sides and 3 angles, have only 3 parts congruent, and they are not all touching. Notice that angle A and angle Z are consecutive angles in our right triangle on the left. Those two angles do not include a known side between them. We have no idea if side ZA is congruent to side HO. Let's look at the remaining angles, angle P and angle T. We know that these two angles must be congruent because of what we said earlier. Given two of the angles, the third angle is found by subtracting the two given angles from 180 degrees. We do not even need numbers for angle Z and angle H. They are congruent. Therefore, angle P and angle T are also congruent. So, if we know that all 3 angles are congruent, and we know that included sides between angles are congruent, then we have the angle-side angle or ASA postulate. Recall that ASA tells us, triangles are congruent if any two angles and their included side are equal in the triangles. Building off that handy right angle, we worked out 2 included angles on either side of the hypotenuse. This allows us to apply the ASA postulate and know that the triangles are congruent. Now, do you need to go through all that every time you want to show 2 right triangles are congruent? No. You can use the HA theorem instead. You cannot show off the HA theorem with something as simple as 2 twin right triangles, but you can with something trickier, like 2 right triangles seeming to slide past each other, like these. These 2 right triangles were constructed from line OA, intersected by line FB, crossing at point G. Right triangle FOG shares a vertex, point G, with triangle BAG. We see that angle O and angle A are right angles, and the little hash marks tells us hypotenuses FG and BG are congruent. This is all we know. Well, we know sides OG and AG form a straight line because they are segments of line OA. We know that both right triangles share point G, creating 2 interior angles, angle FGO and angle BGA, which are vertical angles of 2 crossing lines. Vertical angles are congruent. Now we have another set of congruencies. Let's make a list. Angle FGO is congruent to angle BGA. Hypotenuse FG is congruent to hypotenuse GB. With just the hypotenuse and 1 acute angle, we now release the power of the HA theorem and state that angle FOG is congruent to angle BAG.